Good afternoon, Year 12s. Thanks for coming, guys. So, okay, quick homework today review, because we're going to be having a look at the homework of ionization down a group and across a period. And this will be really good practice for your atomic structure test on Thursday. So I'm going to share my screen. Let's crack on. I just want to get this done as quick as possible. And then I'll come back to the Google Meet in order for us to be able to have a chat and you guys can ask any questions you've got. So usual thing, go to my notes and then I can turn off my camera. Let's see if it crashes. Did it work? Yes, absolutely fine. Right, okay. So here was your homework. Okay, so complete the electronic configuration. So this is, ionization energies across a period and down a group. Complete the electronic configuration. I'm going to do my answers in red. Try and make my writing a bit smaller as well. Complete it for, right, so for magnesium 2+, remember you've got to take 2 electrons away. So 1s2 first and then back to the beginning. 2s2, skip over the, I feel like I want to do it with my table. I always prefer doing it with the table. I don't know if I clicked that quick enough. There we go. So we know that hydrogen and helium are in the wrong place. Hydrogen should be here, helium should be here. Yeah, so, and this is the S block, the D block, and the P block. A reminder of definitions. An S block element is an element whose outermost electrons are in the S subshell. A D block element, an element whose outermost electrons are in the D subshell. And a P block element is an element whose outermost electrons are in the P subshell. Yeah, this is the F block, by the way, and the outermost electrons are in the F subshell. So nice reminders of that, but we've got 1s2. I'm going to shrink down, I'm going to make it red, and then shrink down my pen, because it's ridiculous. So I've got 1s2 for hydrogen and helium. That's 1s2. Right, skips through, and then back to the beginning. There goes 2s2. Skip over, then 2p6. And then magnesium would be 3s2. That would be magnesium as in magnesium metal. But however, this is asking for magnesium 2+, so 2p6, and we're done, finished. Identify what block of the periodic table magnesium belongs. It's the S block. So a neon atom and Mg2+ ions have the same, they are called isoelectronic. Love that word. Isoelectronic. Yeah, give 2 reasons why the first ionization energy of neon is lower than the third ionization energy of magnesium. What? First versus third. Right, so neon's electronic configuration, 1s2, 2s2, 2p6. Oh, okay, I can see what they're doing. Magnesium 2+. So these guys are isoelectronic. They've got the same configuration. However, it is easy for us to then be able to apply our understanding. So even though they've got the same configuration, what we know is that magnesium has 12 protons versus neon having only 10. Yeah, first mark. Second mark, magnesium is smaller. The reason why it's smaller is because if you've got 10 protons and 3 shells, you're going to be there. However, I've got 12 protons and 3 shells. They're going to get sucked in. Yeah, which means the magnesium 2+ ion is smaller than a neon atom, which means smaller, so outer electrons further from nucleus. Further from nucleus. Now, they've got the same shielding, so you can't mention shielding. Nucleus, so harder to remove, more energy to remove. Now, there is another one, which is you're removing it, so, and the last third mark, magnesium is +2 compared to neutral neon. Neon, no charge. So trying to remove an electron from a positively charged ion is always harder. So great question. Reason number 1, you can give whichever, it says just give 2. So I'm going to say the top reason is the fact that magnesium Mg is a +2 ion, whilst neon is neutral. Next, magnesium 2+ ion is much smaller than a neon atom. It's nice to talk about ions and atoms and see the difference. The last one, of course, would be the fact that magnesium has more protons. 3 if you wanted, but any of them will do. There is a general trend in the first ionization energies across period 3, elements sodium to argon. State and explain the general trend. Right, we've learned our graph. Our graph is this. Up, up, dip, up, up. Yeah, the general trend is up. So general trend in is increasing ionization energy, from Na to Ar. Next, explanation. Why? Similar shielding. Now, you can't say same there. That's important. The reason being is it's not the same all the way through. Yeah, this is S block. This is P block. These latter 6 have increased shielding. Not by much, but by a little bit. Yeah, similar shielding. More protons, similar shielding, atom size decreases, so more energy to remove. We're done. So the general trend is up. Next, explain why the first ionization energy of sulfur is lower than that of the predicted trend. Right, sulfur. So sodium, I'm going to switch colors. Sodium, magnesium, dip to aluminium, silicon, phosphorus, sulfur. Right, they're wanting this change. This change, we remember, is this diagram. There's phosphorus, and here's sulfur. 2 electrons in the same orbital. Sulfur, try again. Sulfur has 2 electrons in, you can't do that in an exam, by the way, you have to write 2 electrons. Has 2 electrons in the same orbital. Now, do you know what? We can even pick the orbital. Yeah, so this is the 2p, or is it the 3p? This is the 3p. So this is the 3p. So this is the 3px orbital. Yeah. Sulfur has 2 electrons in the same 3p, same orbital, brackets 3p orbital. It's nice just to do that. 3p. So electron repulsion, less energy to remove. Moving on. I like it. Next. Okay. The electrons are represented by arrows. What property does up and down represent? Spin. Next, suggest why electrons which occupy the 2p subshell have a higher energy level than the electrons in the 2s subshell. They're further from the nucleus. Further from the nucleus. That's easy enough. Explain the meaning of the term first ionization energy. The minimum amount of energy to remove 1 mole of electrons from 1 mole of gaseous atoms. I like it. Give an equation, sodium gas going to sodium 1 plus gas and 1e minus. Give the equation as well, guarantees you the mark. Explain why boron has a lower first ionization energy than beryllium. Back to my table. Right. So we remember my table is just such a wonderful piece of kit. So this is the dip line in the graph, and that dip line is because nitrogen looks like that. Yeah, nitrogen. And then you end up with oxygen, 2 electrons in the same orbital. But we have another dip as well. The other dip is from here to here. And so beryllium. So we've gone lithium, beryllium's harder, and then there's a dip. Yeah, there's a drop. Why? Now this one's much harder, requires a bit more effort. We've got to say beryllium's 3 marks. Beryllium. I can't spell beryllium. Beryllium. Beryllium's outer electron is in the 2s subshell. Yeah, 2s. Row number 2, S block. Yeah. So it's in the 2s subshell. 2s subshell. But boron's outer electron is in 2p subshell. Increased shielding further from nucleus. Less energy to remove. Explain why the first ionization energy of helium is very large. So outer electrons, helium's outer electron is in the 1s subshell. 1s subshell. No shielding. No shielding. 2 protons. Very close to nucleus. Very electron energy level, very close to nucleus. Very close to nucleus. Lots of energy to remove. I like it. Next. State the general trend in the first ionization energy across period 3. Increase. General trend. State how and explain the first ionization of aluminium does not follow this trend. So aluminium's drop. Yeah. Aluminium's drop, sodium, magnesium's gone up, and then there's a dip. Yeah. Magnesium. So it's the same explanation, but this time for aluminium. So magnesium's outer electron in 3s subshell. Aluminium's outer electron. I'd write down the full words, by the way, in my exam. Aluminium's outer electron is in 3p subshell. Increased shielding. Increased shielding further from the nucleus. We never say those two without each other. Yeah, increased shielding, you always tack on therefore further from the nucleus. Yeah, further from nucleus, more energy to remove. Oh no, hang on a minute, less energy. Lol. Less energy to remove. We're done. Give the equation including state symbols that represents the second ionization of aluminium. So second ionization is the state symbol everyone's going to forget. And you're forming 2+. Yeah, there we go. Nice and easy. Don't forget your state symbols. Next, write the general, write an equation including state symbol for the process of the first ionization of energy of sodium. Sodium gas, it can't be a solid, because otherwise the energy and the electrons will go to melting it. And then sodium 1+. Gas and an electron. Nice and easy. Just going to make that N look more like an N. State and explain the general trend in the first ionization. General trend is increase. We realize guys, these are all from papers, and you realize just how repetitive these are. Yeah, I'm just going to check that there's no questions. If it is smaller, doesn't that mean the outermost electrons are closer to the nucleus? Have I made a mistake somewhere? Oh, nuts. What if I said? What if I said, which question? Increased shielding, very close. Which question have I made a mistake on? Similar shielding, more protons, atom size decreases, some more energy. Which question, Louis? Which question? You can tell me in a sec. So increasing, similar shielding. It's nice to see how repetitive this is. Similar shielding. More protons. So atoms decrease in size, more protons. So atoms decrease in size. Electrons closer to nucleus. Put it in. To nucleus. So more energy to remove. Next. State and explain why the value of the first ionization of aluminium, silver, and aluminium and sulfur deviate. I wonder if Louis responded. You wrote it to the side. First question. Oh. First question. The magnesium is a 2+. Okay, increasing ionization energy increasing ionization energy. Explanation: similar shielding, more protons, size decreases, so more energy to remove. So yes, you're absolutely right. Right. So electrons are closer to the nucleus. Yes. You can add that there if you like. Don't mind. Feel free. And then I wrote it to the side. Smaller, so outermost electrons are closer. Thank you. There's my mistake. Closer to nucleus. Thank you, Louis. Oh, funny. Next, how the value deviates from the trend. Sulfur is how the value deviates. It's lower than expected. Lower than expected. Yeah, so we remember our graph again reappearing. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur. So we've got aluminium and sulfur that are both lower than expected. We were expecting them to be there, but they weren't. They're actually lower. So they're both lower than expected. Explanation for aluminium. Outer electrons have entered 3p subshell. Increased shielding. You see how repetitive this gets and why the exercise is so useful. Yeah, increased shielding further from nucleus. Less energy to remove. Less energy. Sulfur, 2 electrons in same 3p orbital. Electron-electron repulsion. Less energy to remove. I like it. What is meant by the term first ionization energy? The minimum amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms, given an equation. I'll write it down anyway. Let's do first ionization energy of sulfur. Aluminium. Gaseous, so easy. Gaseous atoms going to 1 plus gaseous ions, the minimum energy to remove. Don't do it the way I've just done it there. Do it properly in your exam. Minimum energy to remove. Next, what is the maximum number of electrons that can be accommodated in an S subshell? 2. What evidence from the diagram supports your answer? Aluminium's deviation. Aluminium is lower than expected. So electron has entered a different energy level. What evidence in the diagram support that the 3p subshell is higher than energy than the 3s? Ooh. What evidence? Because Oh, what evidence from the diagram supports the fact that the sp subshell is higher in energy than the 3s? Because the nightmare about that, I can tell you what the answer is. The answer is this: the general trend is off. What that means is the whole thing has been shifted out of sync. Because what we would do is, if this had all been one energy level, it would have done this. But instead, all of these are lower than what we expect. Which means it must be further from the nucleus. I know that they're higher than the sodium magnesium ones, but it doesn't actually matter. They're not following the pattern. Go on, that one I'm going to have to check. Wow, first question that I really want to see a mark scheme. All ionization energies beyond magnesium are lower than expected. That's a really interesting question. 1 mark. What evidence from the diagram? So I need that one. I'm going to have to, guys. Any more questions? No, Louis hasn't asked me anymore. What evidence from the diagram supports that there are no more than 3 unpaired electrons to accommodate? It's the dip. They're saying that's this one, sulfur. Sulfur's decrease. Sulfur decrease. And then I just want to say the same thing again. Sulfur, I want to see the mark scheme for that one as well. Sulfur has 2 electrons in same orbital. So electron repulsion. Less energy to remove. That one's very interesting. There's the question which I now need an answer to. Such a shame that I didn't write down what all the papers were that I stole these from. What I need to do is I need to Google that entire question. Louis, can you do me a favor? Can you just type in that entire question right there and then click on the Edexcel paper that turns up and tell me which Edexcel paper it is? That would be really, really handy, Louis. Saves me having to do it. It means I can continue. Explain why the atomic radius across period 3 sodium to chlorine decreases. Okay. More protons. Now, this is interesting. They've chosen sodium to chlorine. Okay, that's fine. It goes all the way. More protons. Similar. You can't say the same. Similar shielding. So, electrons in outer shell, outer energy level, have greater attraction to the nucleus. More protons, similar shielding, greater attraction to nucleus. Still waiting on Louis to post that answer for me. That's okay. Next, the diagram below shows the trend in first ionization completed. Draw the crosses on the graph. Right, so there's our normal pattern. This one was from a previous shell. They've linked them together. Aluminium, right, hang on a sec. So we can clearly see that this one is below that one, but above that one. Right, the next one needs to be above magnesium. Yeah, I'm going to put it about there. I think that's a very reasonable up. And it's gone up by 2.5 squares. So if I then go to another one to be there. What I'm trying to do is I'm actually trying to follow the same gradient. Then there's a drop, and that drop there was, trying to read off that drop with all my lines on it, is about 1.5 squares, if not 2. So put it about there. Oh, sorry. There we go. Very reasonable. Oh, first thing that came up, page 8 and 9. Louis, I needed the exam paper. Do you want to tell me what the Edexcel exam paper was? Lol. Anyway, so draw on those 3 marks. Wowzer. It's a lot of marks, that. Be interesting to see the mark scheme for that one as well, just to see how much leeway they give you. Next, write an equation that illustrates the process of the first ionization energy of neon, neon gas, going to neon 1 plus, gas, plus an electron. Don't forget your state symbols. See what Louis said now? No response, it's okay. Explain why the first ionization energy of neon and that of magnesium are both higher than that of sodium. Okay. Oh, that's really clever. Oh, I like that. Haven't seen one of those in a while. They've said that neon is above sodium and that magnesium is above sodium. Now, that's a really interesting point to make, isn't it? So why is neon so much higher? Because it's got less shells. It's only got 2 shells. Yeah, so explanation for neon. Neon outer electron in the 2p subshell. And then magnesium, and then sodium's is in 3s subshell. More shielding, so less energy to remove. Next, why is magnesium higher? Now they've got the same shielding, but now magnesium's got an extra proton. Yeah, because the magnesium, they're in this, the outermost electrons both are in the 3s. So both Na and Mg have outer electron in 3s subshell. Same shielding. However, Mg has an extra proton. So smaller than Na. So more energy to remove. Clever question. Really nice. Really love that. Really good. The first ionization energy of aluminium is lower than that of magnesium. Aluminium's outer electron in 3p subshell. Magnesium's outer electron in 3s subshell. Aluminium has more shielding, so less. It's got more shielding further from the nucleus, further from nuke. Got to go the whole way. Further from nucleus, less energy to remove. Did Louis manage to find out that paper yet? I looked it up and it said AQA January 22. Oh, okay, it's an AQA page 8. No way. Right, what does the mark scheme say? AQA Jan 22. That's interesting. Oh, went for an AQA question, did I? Intriguing. Let's have a look. PMT, please. You realize that it makes no difference, folks. In fact, they make you a better chemist. You should have a look at the Cambridge International multiple choice. God, they're hard. It's a really, really great question. Like, some of the questions there are outstanding. AQA Unit 1, January 2002. Carnarvon. Because it doesn't go that far back. How fascinating. That means it's been repeated by a different exam board, or maybe the same exam board. How fascinating is that? I definitely didn't get it from there, folks. Not unless I went back to Legacy. Legacy Unit 1? No, it doesn't go back far enough. That's hilarious. It's been repeated word for word by another exam board or by AQA later on. What was the question? You guys aren't going to help me very much here, are you? I was really hoping you were going to find it, so I didn't have to search for it. No one else managed to find it. This is a nightmare because I can't even go back that far. Like 2002 is bonkers old. Can you see the link, sir? No, I can't. I can't see the link. Oh no, unhide show. I don't know where the link is. Page 8. No. I don't know. No, I can't see the link. How annoying is that? I wonder why that is. Haven't got a clue. What a nightmare. Oh, well done. Someone's just sent me it on the chat. Yes. Wow, this is like an ancient paper. Holy moly. I want to see the mark scheme for that. Oh, it's handwritten by somebody as well. How fascinating. Let's have a look. I haven't gotten back. There's another exam paper that has used the exact same question because I can't even go back this far. There it is, though. Number of protons, electrons in shells. Take the meaning of the term electronegativity. Didn't want that. What evidence? The two elements. The two, or Mg before the drop. Okay, I think I said something similar, didn't I? That there was a drop. The evidence that supports part D. What is the maximum that can be accommodated in the... It's not quite exactly the same, is it? It's not even in the same format or anything. It's really clever, though. I do love it. So it's word for word. It's crazy. What is the maximum number that can be accommodated? 2. Let's go back to that paper. 2. I like it. Next. Evidence, 2 elements before the drop. 2 elements before the drop. Aluminium is lower than expected, so electron has energy of a different energy level. So electron has energy. I've written that really badly. I said something different. Aluminium is lower than expected. Yeah. So electron has more energy. So in a different energy level. So in a different energy level, further out. Yeah, 2 before the drop. Okay, what was the next one? What evidence is there that the 3p is higher? Right. What evidence from the diagram supports that the ionization energy of aluminium is smaller than that of magnesium? It's the same answer. Isn't that fascinating? So that's really interesting. I don't know if I would all ionization energy beyond are lower than expected. Yeah, I'm tempted to give it. It's the aluminium that's the drop, isn't it? It's that one that's clear. It's telling us that because that one is lower there than expected, that gap there, yeah, tells us that it must have gone into an energy level further from the nucleus. Yeah, which means it requires less energy for me to remove it since it's gained more energy by being further out. So I wouldn't give myself for that. I'd probably just say I need to make sure, yeah, the evidence focus AL drop after Mg. Yeah, I like it. Really good question. Man, what evidence from the diagram supports the fact that there are no more than 300 paired electrons? Yeah, the same drip. For same drop, the fall from P to S, and then from Al to P. Oh, interesting. For second mark, idea of block 3 elements. Interesting. What did I say? 2 marks that was. Sulfur decrease, full stop. Sulfur has 2 electrons in the same orbital, so electron-electron repulsion, less energy to remove. In the same block, idea, fall in energy from phosphorus to sulfur, or discontinuous in trend. From aluminium to phosphorus, there are 3 additional electrons. Idea of a block of 3 elements. Weird. That's strange, isn't it? Oh, the block of 3. Yes. Yes, block of 3. Yeah, 1, 2, and then 1, 2, 3 blocks of 3, and then drop block of 3. Yeah, and they're saying that this, of course, is the explained. There's the first block, and then there's the second block. Yes, that's clever. Anyway, have I come to the end of my homework? I have. Wowza, I'm done. 15 minutes early. That was a long bit of homework. That was like 46 marks or something. It was epic. Right, homework scores. Winner, ionization, group, period, homework out of 42. Right, guys, add them up, please. What I'm going to do is I'm going to end the YouTube video now, since there's no point in me remaining on it, and I will rejoin you guys. Right, what I need to do is I need to minimize that, and now I need to turn my camera back on. It's a bit ridiculous, this. All I need to do is buy a better laptop. But the problem is I need to be able to write on it. This is an i7 Surface Pro, and it's just still a bit rubbish. There we go, folks. Right, I don't know how to make the Ehan's thing disappear. I haven't got a clue. Oh no, I don't know what I've done. Anyway, guys, have a great rest of your day, and I'll see you over on the chat.